In this video, we're going to take a look at Dalton's law of partial pressures. So another great preview of the material video can be seen here with some excellent visuals. Let's go ahead and take a look at what Dalton's law of partial pressures mean. We can see it defined and also we can see it mathematically. So we say that the total pressure of a mixture of gases that aren't reacting with each other, that are just kind of swimming around together, is going to be equal to the sum of the partial pressures of the individual gases. What does that mean? It sounds confusing, but essentially, let's say I were to take some oxygen. Its pressure is 3 pascals, and nitrogen, 2 pascals. And I were to combine those together. The oxygen providing 3 pascals of pressure, the nitrogen 2 pascals of pressure. So the total pressure of this mixture is going to be 5 pascals. So we can say that in here, oxygen is providing some pressure. It's providing 3 pascals. That would be the partial pressure of oxygen. And nitrogen is providing pressure, is providing 2 pascals. That would be the partial pressure of nitrogen, to give us the overall pressure of 5 pascals. So it basically means that if you mix gases together, the total pressure is going to be equal to the pressure of that the individual gases sort of provide to that mixture. So your total pressure is equal to partial pressure of gas 1 plus partial pressure of gas 2 plus partial pressure of gas 3, as many gases as there are there. And you would add those all up to get your total pressure. And it is important that they're non-reacting gases, because if they react, then you have technically fewer particles of gas there if they combine together in a synthesis reaction, for example. So let's take a look at what this means for us in some practice problems. Let's go to our handouts. So our handouts over here for Dalton's law of partial pressure. So a tank used for scuba diving has oxygen at a partial pressure of 2.8 times 10 to the power of 3 kilopascals, and nitrogen at a partial pressure of 1.1 times 10 to the power of 4 kilopascals. What is the total pressure? So PP stands for partial pressure. Another way you can write this, just to show you before we do this problem, or actually as we do this problem here. So we want to do our total pressure, PT, is equal to the partial pressure of all the gases added together. So partial pressure of oxygen, PO2, plus partial pressure of nitrogen, N2. We have our partial pressures of oxygen and nitrogen given to us. Partial pressure of oxygen is over here. Partial pressure of nitrogen is over here. So we're simply adding these together. So partial pressure total is equal to 2.8 times 10 to the power of 3 kilopascals plus 1.1 times 10 to the power of 4 kilopascals. You need to make sure that the units of pressure are the same. So if you have different units of pressure, make sure you convert them as needed. And we get, so you can go ahead and do that. So 2.8 times 10 to the power of 3 plus 1.1 times 10 to the power of 4 gives you about 1,000 or 13,800. So that would be and it's kPa, so units are consistent there. But we have to maintain the same number of sig figs. So we want to have 2 sig figs max. So that's approximately, we could say 14,000, or you could write down 1.4 times 10 to the power of 4. Oh, and then kPa. Do not forget those units. All right, so there's how you would calculate total pressure from the partial pressures provided to you. So over here, for example, in the above example, in the starting visual, if we want to do the total pressure, we would do pressure of the oxygen, partial pressure of the oxygen, plus partial pressure of the nitrogen. In this case, it would have been 3 pascals plus 2 pascals gives you 5 pascals. Let's go ahead and try our next example here. The total pressure of a mixture of hydrogen, helium, and argon is 99.3 kPa. If the partial pressure of helium is 42.7 kPa and the partial pressure of argon is 54.7 kPa, what is the partial pressure of hydrogen? Okay, so first of all, we have a mixture of gases. We know that the total pressure is going to be equal to the partial pressure of all the gases in there. So pressure of hydrogen, partial pressure of helium, plus partial pressure of argon. Now we're given the partial pressure of helium and argon, but we're looking for the partial pressure of hydrogen. So we're just isolating from, we're trying to solve for partial pressure of hydrogen. Now we also need the total pressure. That's also given to us. It says the total pressure is 99.3 kPa. So we can rearrange this. We can get the partial pressure of hydrogen is going to be equal to the total pressure minus the pressure of helium minus the pressure of argon. So you're basically just taking away the pressure of helium and the pressure of argon, the partial pressures of them, from the total pressure to get the remaining partial pressure of hydrogen. So that's going to be equal to 99.3 kPa minus, I'm just going to combine them together here. So it was 42.7 plus 54.7. So I'm doing minus those kPa. And so it's going to be 99.3 minus 42.7 minus 54.7. And we get about 1.9 kPa. We have the same number of decimal places, one, so 1.9 kPa. That would be the partial pressure of hydrogen. Now, to make sure that this actually works out to be the same, to be correct, we can add all the pressures back together to see if it adds up to the total there. So 42.7 plus 54.7 plus 1.9, and we get 99.3 again. So that means that we have the correct answer. So that's our final partial pressure of the hydrogen there. In the next video, we're going to take a look at some laboratory practical applications of this partial pressure. It's applicable in many situations, where we'll take a look at a specific application called collecting gas over water.